We Earthlings have fired numerous probes and satellites towards the red planet. An invasion of sorts, not for conquest, but for knowledge. What happened to Mars? Is there or has there ever been life on the planet?
A fundamental question that needs to be answered is life as we know it on Earth, even the simplest type of microbial life, unique? If we were to go to Mars and we were to find evidence of early microbial life, or maybe even present life that somehow survived in the near surface, would it be the same as the early life that developed on Earth? That's a very fundamental question. Does life emerge generally in planets where the conditions for life are favorable, if we find out that they were favorable on Mars? Or might life take its own unique path in different environments and turn out differently?
We have bombarded Mars with satellites and landers, but there have been more failures than successes. The Soviets established 2 Mars orbiters, while NASA landed 2 Viking landers carrying complex analytical laboratories and searched for signs of microbial life. Their findings were inconclusive. Further missions to Mars still had a high mortality rate, but the successes were outstanding, with robotic probes operating for years beyond their initial missions. In fact, Mars is a planet occupied solely by robots on the surface and satellites peering down from above. All these instruments perform admirably in their specified fields of endeavor, giving us a much clearer picture of the planet and its history. The science was following the water, what happened to it, and where it is now.
Thanks to the specific instrumentation on board the mission, we are able to tell us what kind of ice did we find. And the result is that there is a mix of CO2 ice, or carbon dioxide ice, and water ice. And it's very important to characterize it, especially for the water ice or frozen water, because one of the main objectives of any mission to Mars is to trace the water on Mars in every form, liquid if possible, solid, water vapor. So it's very important to study the ice because it's one of the reservoirs of water on the planet.
The science was conclusive. There was water on Mars. There were ancient lakes and rivers, even an ocean. We needed to learn more. With the advancement of analytical technology, computer power, and robotics, a new rover was constructed. Big, complex, and heavy, it required a new way to land on Mars safely. Engineers came up with a system that couldn't be fully tested here on Earth. It required a lot of things to happen correctly, on time, and in order. This was the Sky Crane, and the rover Curiosity was the first to try it out. A controlled re-entry with heat shield, aerobraking with a parachute, all pretty standard. Then a rocket-powered Sky Crane drops from the aeroshell and gently descends toward the surface, spooling out the rover below on cables. The rover touches down, cuts the cables, and releases the Sky Crane to fly off and crash harmlessly. The Curiosity rover has been an astounding success, traversing the terrain for over 10 years, taking samples, drilling and studying rock formations, zapping samples with a powerful laser, and photographing its progress.
Now, in the belly of that rover is an instrument called SAM. It's an instrument suite that has a couple different instruments in it that allow us to look at different types of gases. It helps us understand the chemical composition of the atmosphere and the end of minerals that might be found in the rocks and the soils on the surface. In particular, it helps us identify organic molecules that might be present.
So the sort of evidence we're looking for, sorts of signatures of past life that we would be looking for would be signatures of microbial life. So not realistically looking for dinosaur bones and that kind of thing. If life ever existed on Mars, we expect it to have been microbial, microorganisms.
Orbiters, including Mars Odyssey and Mars Express, have been hunting down life as well from orbit.
After 10 years of mission, we have achieved a global view of Mars, and then we know at every location on the surface if you find some special minerals or not. So we have really the global view that tells us the history of Mars. Mars Express has, for the first time, detected methane, and also the concentration in the atmosphere vary from a place to another, from a season to another. And this discovery has been very debated in the scientific community, because in fact methane should not be there because it's being destroyed in the atmosphere by the ultraviolet radiation. So if methane is there, there must be a source of methane, and for the time being the origin of this source is largely unknown.
However, with Curiosity prowling around Gale crater, it too detected seasonal methane.
Now, methane has been found previously in the Martian atmosphere by both Earth-based telescopes and spaceborne orbiters. But this is the first time that we've actually seen a sharp increase and decrease in the abundance of methane in the atmosphere in Gale crater. What this really means is that present-day Mars is an active environment.
The big question is, what is the origin of this methane now being released? The two principal areas are, first, by analogy with the Earth, it could be released and produced initially primarily by biology. This would be microbial activity acting on certain chemicals below the surface and then producing methane as a byproduct. But of course we can't state with certitude that it is biologically produced. And so we also consider geochemical mechanisms in which carbon dioxide is actually combining with water and producing methane under very high temperatures and pressures. And that methane can then be released into the atmosphere separately.
Now, at this point, we don't have enough evidence to tell us whether or not the organics we're finding are biological or non-biological in origin. There are several viable non-biological explanations, including this organic material could have come down from space, from meteorites or comets, or organics can be formed by geological reactions in the rock itself. Now, what's exciting about this discovery is it gives us new hope in the search for chemical evidence of life. We found the organic material. Now, the next step is trying to figure out what its origin is.
Main engine start, ignition, and liftoff of the Atlas V with Maven, looking for clues about the evolution of Mars through its atmosphere.
The latest NASA orbiter mission is Maven. Launched in November 2013, it made orbit 10 months later.
Maven is the Mars Atmosphere and Volatile Evolution mission. Our goal is to study the role that loss to space has played in the history of the atmosphere. Where did the water go? Where did the CO2 go from the early planet? These are important questions to understand how Mars went from an early warm, wet environment to the cold, dry environment we see today.
There's evidence of water flowing on Mars at one point in time, perhaps even oceans on Mars. And what happened that it's so barren at this point in time? And a key part of that is the atmosphere, and it's a much thinner atmosphere than what scientists believe it was at one point in time. So the stripping away of that upper atmosphere, that's what Maven is going after, the climate change at Mars.
One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. The sun constantly emits high-energy photons. When these enter a planet's atmosphere, it can crash into a molecule, knocking loose an electron and turning it into an ion. When this happens in the presence of a magnetic field, the ions are captured and spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, these ions are carried away. Depending on where they form, other ions will not be carried away but will hit the top of the atmosphere. These ions crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. As this process continues over billions of years, Mars' atmosphere has disappeared, and along with it, the water. How much water has Mars lost this way?
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
Water naturally carries a heavy isotope of hydrogen, deuterium, which remains trapped in the water cycle while normal hydrogen is lost to space. Detecting the amount of deuterium enrichment tells us how much water has been lost.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.